Before we get started, I want to set the stage. I want to set the context and help you understand how we structured this entire series. We have been delivering multiple webinars, and most of them have been covering the cutting edge technologies like Internet of Things, big data analytics, machine learning, and other variety of topics. But this series is slightly different. It is not just one of the sessions on Docker or containers, but if you attend all the 6 sessions that we have lined up for you, you will get a very thorough understanding and a great overview of cutting edge technologies in the container landscape. And as I mentioned, by end of this series, you'll be very confident of dealing with Docker, which is the primary platform for containers, and Kubernetes, which is the de facto platform for orchestration. So don't look at this as yet another webinar and just attend and don't just give up in terms of the follow-ups. Go ahead, try out the tutorials we are going to share with you. And this is almost like a curriculum with hands-on lab that you can practice at your own pace. So the way the webinar is structured is, I'm going to introduce a concept, what we have done earlier. There is less of theory and more of demonstrations, followed by the lab manual that you would receive. So I'll introduce a concept, followed by questions are primarily covered in the tutorial that you would receive. So the idea is you watch the webinar, a section of this, pause it, practice the same set of commands that are exactly covered in the demo, and get a thorough understanding of the technologies that we are covering. So by end of each session, you would have mastered certain key concepts that are very essential to get the skills of containerization. And going forward, containers are becoming very important in terms of cloud native applications, microservices. Find this useful, and you also love the format that we are bringing in for the first time. So without further ado, let me get started. So this is the first session in this series, which is all about installing and configuring Docker. By end of this session, you will be not only installing and configuring Docker, but you would launch your first container. You would know how to deal with images. In fact, you'll also build your first custom image and push it to a private registry. So we are lining up quite a few concepts in this webinar. So pay attention and gain from the concepts and the value that we bring through this webinar series. So what exactly is Docker? We have done multiple webinars on Docker earlier, so I'm not going to cover the background or the motivation for containers, but I want to briefly touch upon the Docker architecture, followed by launching the containers. And even if you're not very familiar with Docker, you will still find this very useful. And then we will learn how to deal with images. And finally, we will learn how, and all of these will take place within a DigitalOcean droplet. So the idea is to help you build a solid foundation of dealing with containers in the cloud. Though Docker is available on Windows and Mac, I'm primarily covering the concepts related to Linux that were deployed in the cloud, which is DigitalOcean. So virtual machines versus containers. There has been a lot of discussion and debate on VMs versus containers. So the primary difference between virtual machines and containers is the way it is layered. So if you take a look at VMs, predominantly available through KVM, Xen, or any of these hypervisors, you notice that there is physical infrastructure, then there is a hypervisor, and on top of that hypervisor, you have multiple virtual machines. And every virtual machine has its own operating system, its binaries and libraries, and then the app itself. So the components that are very, very important for the application, and the application expects them to be in place, are packaged within the virtual machine. And if you are launching multiple VMs, the delta between one VM and the other VM is basically the app, but in majority of the cases, the guest OS and the libraries are going to be repeated. But unfortunately, you cannot share them because every VM is a standalone, isolated unit of deployment. So even if you're launching multiple containers running the same application, it has to run in its entirety. And VMs are slightly heavier, they are bulky, they take longer time to boot and scale, and there have been multiple concerns about the speed at which you can scale in and scale out virtual machines. So when it comes to containers, the architecture is fundamentally different. You still have the physical infrastructure in terms of a bare metal server or a virtual infrastructure. Then you have a host OS, which is predominantly Linux. And on top of Linux, you have the container management layer, which is Docker. And on top of Docker, you would run multiple containers. But unlike virtual machines, in containerization, you will actually share the operating system. So the delta between one container and the other container is primarily the libraries that are very specific to the application packaged as a container and not the entire OS. So you are not repeating everything for each container. Instead, you'll only package what is absolutely essential for each of the applications. And those applications along with their dependencies are packaged as smaller containers while the underlying operating system is still shared. And the interface between what is managed by Docker. So Docker is a system-wide layer that is going to help you manage containers. And containers are much lighter when compared to VMs. If a VM is almost like a few gigabytes, most of the times containers are only a few megabytes, which makes it very lightweight and also portable. And the best thing is Docker also brings multiple Linux flavors onto the same level playing field. For example, you can develop an application on Red Hat Enterprise Linux, package it as a container, but very easily launch it on Debian. So across multiple Linux flavors, you can launch the same set of containers with no modifications. So it basically brings multiple Linux flavors into the same level playing field, making it easy for you to port applications across multiple flavors. And when I say multiple flavors, it is just not confined to a standalone Linux machine running in your environment, but you can create a container in one cloud, toss it around and launch it in another container, and completely productionize the app in a very different cloud environment. So advantage of moving to containers. Now, taking a closer look at the Docker architecture. So installing Docker is very straightforward, which I'm going to cover in the very first demo. But if you look at the way this is packaged, Docker has three components, three essential components. The first one is called the Docker engine. And this is the workhorse of the Docker platform. It runs in Linux as a background process. It exposes REST API, and it's also responsible for dealing with the underlying kernel. So the Docker engine is the layer between the containerized applications and the operating system. It negotiates various things with the kernel. For example, every time you ask for memory, CPU, storage, and networking capabilities, it is Docker engine that is negotiating with the operating system to get the right level of resources you have requested for. So this engine is exposed as REST API, and you can directly consume this, but to make it easy for you to deal with this API, Docker also ships a set of command line tools. And these tools are developed in a way that they primarily interface with the Docker API. So when you run any of these commands, you are basically pointing them to an endpoint, which is nothing but a REST endpoint exposed by the Docker engine. And these tools make it very easy for you to run a variety of commands to manage the lifecycle of containers, manage the lifecycle of images, storage volumes, overlay networks, and so on. But remember, the tools themselves are not very useful. They are useful only when they are pointed to a running Docker engine. And the other thing to understand and notice here is the tools can be run outside of Linux. It is perfectly fine to have the Docker tools run on macOS 10 or Windows, while the engine is running within Linux. And obviously, Docker engine cannot natively run on any other operating system other than Linux, but you can run tools on any other platform while you point them to a running Docker engine, which which is primarily on Linux. Since Docker deals with a set of images, and images when they are launched turn into containers, you need a repository. You need a centralized location to store all the images from which you are launching your containers. And that database of images is known as Docker Registry. It is responsible for storing and distributing the Docker images. And this registry, as you might guess, can be available publicly, or it could be deployed in private environments. In a large organization that is dealing with hundreds of containers, it doesn't make sense to keep them away from the Docker engine. So we need to keep the registry closer to the Docker engine, because when you pull an image and launch the container, you want minimal latency between the engine and the registry. And also it is more secure to run the registry in private environment like an enterprise data center or within your own virtual network running in the cloud. So the Docker registry can be either public or private. The public version of Docker registry is called Docker Hub, and this is hosted and managed by Docker Inc. But you can also pull an image, which is actually the Docker registry image, and run it within your own environment. And this Docker registry can run on a variety of backends, variety of storage backends. So you can actually mount a variety of file systems and point Docker registry to any of the supported file systems. So at a high level, there are three components: Docker engine, Docker tools, and Docker registry. So with this background, it's time for us to go ahead and install Docker. So let me take you to the environment, and this is my very first demo. So I have gone ahead and launched my droplet. So this is a standard DigitalOcean droplet running in the Bangalore data center. It has got a public IP address, and we are going to basically run a set of commands. And this is running on Ubuntu 16.04, which is a very popular Linux operating system among the open source developers. So how do we install Docker? Well, there are a set of commands particularly targeting the the Ubuntu build. So we first start by making sure that we don't have any older versions of Docker engine. Then we add the appropriate repositories, the packages, and then we go ahead and install what is called as Docker C, which is the Docker Community Edition. So by running this set of commands, you will end up installing Docker. So let me switch to the command line. So here you will notice that I am not connected to the droplet anymore. Never mind. I will SSH again. So let me grab the IP address. Because the SSH is already configured, I can directly get into the droplet. Excellent. So now we are inside the droplet, and to just make it easy, I have copied and pasted the same set of commands that you have seen in my editor into a shell script. So let me make sure I can execute this script. So I'm setting the right permissions, and then I go ahead and run this single shell script, which will basically install Docker. So this process, we'll have Docker installed. It just takes a couple of minutes. While this is going on, I want to point you to something else. DigitalOcean has something called one-click deployments or one-click droplets. So when you go to the droplet and click on the create droplets, you'll actually notice that you can launch plain vanilla droplets, which are like the blank slate VMs, or you can actually go to one-click apps. And the best thing is there is a Docker image or Docker one-click app that's available. You can just select this and follow the same steps like the remaining droplets. And in just a few minutes, you'll actually have a complete droplet fully configured with Docker. But for the fun of installing and to make sure you understand the steps, I have gone ahead and deployed it manually. But if you are using DigitalOcean, you can also launch the Docker droplet with the one-click app droplet. Perfect. So now we have gone ahead and installed Docker. So how do we verify? Well, just type Docker info And this is going to show you a lot of information about Docker. So currently there are 0 containers. Obviously, this is the very first time that we are launching Docker. So we don't have any containers. There are no images. The other way of making sure that everything is fine is to run this command called Docker version. And Docker version shows us what is the client version. Client is basically the tools that I have explained. So for example, the Docker command in itself is a tool, it's a client. And the server is the background process that we have just installed. And both of them are running the same version, which is the 1709 Community Edition. So Docker is now installed, as simple as that. Of course, if you want to do it on your Windows or Mac, you can download the installer and run it, and this is going to be available on your local machine. All right, so that was the very quick but a simple demo of installing Docker. Once we have Docker in place, what else can we do? Well, it's time for us to launch our very first container. A container, as I mentioned earlier, initially becomes available as an image. So if you're familiar with virtual machines, you know that there is a VM template and then there is a VM. So the runtime of a VM template becomes the VM itself. And similarly, the runtime of a Docker image becomes the container. So we need to start pulling the right images. So you have a huge database or a repository or a collection of images centrally stored, and it contains maybe millions of images because we are dealing with a public registry. You may have far lesser images if you are running a private registry. But irrespective of where you are pulling it from, you will actually pull the image and then run it locally. So the next step for us is to launch our container. So let's go ahead and launch the container. But before we launch the container, I want to introduce what is called as the Docker Hub. So if you go to hub.docker.com, you'll notice there are a lot of these images, and these images are officially maintained and managed by Docker Inc., the company that actually develops Docker. So as you notice, there are popular repositories. Repositories are nothing but collection of multiple images, because one image can have multiple versions. So a collection of similar images but with multiple versions is actually called as a repository. Think of this like a GitHub repo, but more optimized for storing Docker images. They share a lot of similarities. If you look at Nginx, it has 10 million plus pulls. That means developers have been using it more often. Alpine is another flavor of Linux, and that is enjoying a lot of attention. So you see more pulls for that as well. And then there is Apache's own web server, which is called HTTPD, and that is also one of the top images. So you'll see there are a lot of these popular images that we can explore. So this is the Docker Hub. You can also go ahead and sign up to get your credentials, because eventually when you want to store your own images, you need to install them. You need to have the credentials. So it's a good idea to go ahead and sign up with Docker Hub to get your own username and password. All right, now we are back to the command prompt. You can also perform the same search. For example, here I can perform a search on Apache, and it should show us, the official image of Apache, which is HTTPD. You can pretty much do the same thing. So Docker search HTTPD will show us a lot of results. Even if you bake a new image and push it to Docker Hub, that will show up here. But we are interested in the official one. So you'll actually notice that this one is qualified as official. Then there is an OK, which means it is an indication that this is the official image that we are interested in. This actually represents the number of stars. And as you notice, this has the maximum, which also confirms that this is the official Apache server that we are interested in, right? So that's how you perform searches from the command line. One way of doing it is from the browser. The other way is using Docker search command. So let's also search for another very simple image called Hello World. So if you're a developer, how do you get started? It's always by executing hello world, and Docker is not an exception. So let's run hello world as our very first container. So you'll actually see that there's an official hello world container with 400 stars. So let's go ahead and execute this. How do we run hello world locally? The very first step is to pull hello world. So Docker pull followed by hello world. So this is going to get the latest hello world image from Docker Hub, which is referred as library, and it now becomes available on our local environment. So now if you actually do Docker images, a command that will show you what we have on the local machine, this will confirm that we have an image called hello world, and guess what, it is as small as 2 KB, it's 1.84 to be precise. So we have the image. What's the next step? Well, all we got to do is Docker run followed by hello world. Now this is going to confirm that everything is perfectly installed. So it actually prints hello from Docker followed by a lot of things that you can actually do as a follow-up. So this confirms that the Docker client contacted the Docker daemon, and the Docker daemon pulled hello world, and it created a new container from the image, and the Docker daemon streamed that output to the Docker client, which is sent to your terminal. So a lot of things went through with this very simple command of Docker run. And if you don't have the hello world image on your local environment, a Docker run would automatically pull. So you need not really first pull and then run. When you actually do a Docker run, it checks whether it's available locally or not. In case it is not, it goes ahead and pulls it. All right. So now let's actually go ahead and execute another command. So this time we are interested in launching a HTTPD, which is Apache Web Server. Since this is not available on our machine, it's going to first pull it and then try to execute. So now Docker run is first doing a pull. So in just a few minutes, you'll notice that we are going to get the image to the local environment, and then this is going to be running on our machine. All right, so now this is running. You'll actually notice that these are the Apache logs, and it looks like it is running. There are no error messages, and everything seems to be fine. But guess what? We still cannot access this. We cannot really hit the browser and type the IP address and get what we want out of it. The reason for that is we actually haven't exposed a very important thing, which is the port. So it's time for me to basically launch the same command with a couple of additional switches. Now I want to introduce some additional parameters related to the Docker run. So when you are launching a web server, there's no point if the port is not open. So to make sure that the container port 80 is available on our droplets port 80, we do a port mapping. So -p is basically port forwarding from the host container running within the droplet. That's what is -p represents. Then we're also giving a name, because it's always better to give a friendly name to the container. Otherwise, Docker will go ahead and assigns a random name, and it makes it difficult for us to refer to it after we launch the container. So we have given it a name. And finally, I have given another switch called -d. And this instructs Docker daemon to run the container in detached mode. Otherwise, we'll end up, we have to launch another terminal, another session, and start continuing our work. So it's a good idea to launch the container in a detached mode, which will continue to run in the background without us launching another terminal, another shell, another session to test it and to continue the remaining commands. So now we have a meaningful container running on our system, which is the Apache web server that is exposed on port 80, and the name of this container is web. So let's go ahead and launch this. This time, we are back to the command prompt, and you actually see a long string, and this represents the hash of the running container. And when you actually see this, it's an indicator that Docker has successfully launched the container. And how do we verify this is happening? So the way this works is we actually run a command which is docker ps, pretty much like a ps command of Unix. And what this does is it's going to confirm that we have the actual container running in appropriate ports. So port 80 is forwarded to the container, and this is the container ID. We also see the name of the container, which is web. And behind the scenes, the container has launched this command called HTTPD foreground. So we can by using curl. So curl is a command to basically send HTTP request to command line. So let's go ahead and do a curl localhost, and this confirms that Apache is in fact running. So this is our first meaningful containerized application, which is running an Apache web server, right? Because we're talking about the container lifecycle, so we have first pulled the image, then we ran it. So it's now time for us to stop this container. So when you actually type docker stop, you have two options. One is to basically give the ID or the hash of the running container, or you could also give the name. So I prefer to give the name because we have named the container. So docker stop web will go ahead and stop the container. So docker ps will not show the running container anymore. You can also permanently remove. For example, if you want to launch it again, you can always use docker start and web server is back in action. So if you want to permanently get rid of this, you can first stop the container and then remove it altogether by running docker rm web. And now when you actually do a docker ps, nothing is shown. So that's how you basically pull, run, stop, and remove containers. And this is all about the life cycle of a container. This is a quick way of learning how to deal with containers. All right. So now we have launched our first container and we have tested it. It was working because we could see a response, a HTTP 200 OK from the web server. Now we need to go beyond that and make this more powerful and more meaningful. And the way we do that is to basically make sure that we add additional capabilities. So one of the first things that we need to learn is containers have ephemeral storage. So ephemeral storage means that whatever is stored within the container will go away with the container. So it is not permanent. So the data that you store in a container will be available only as long as the container is available. The moment you terminate a container, the data or the content that you put inside that will also vanish. So that's not very useful. For example, how do you run databases? How do you run web servers where you're uploading some files and you want to do more complex deployments that deal with persistence and storage, and you need to have additional components that are stateful, where you need to store, preserve the data and retrieve it for later interactions. So to make sure that we bring persistence to containers, Docker offers a concept called volumes. And each volume can be implicitly or explicitly mapped to a host directory. So basically what this means is if you're running it on a VM or any host, I use the term VM and host interchangeably because we are actually running it in the cloud. And here VM or droplet or host primarily point to the same environment. So we actually create a directory or a predefined folder on the host operating system, which is the Linux operating system, and then expose it to the container that we have launched. So even after the container is terminated, whatever is returned to that directory will continue to be available. And later on, if you launch another container and point it to the same directory, it can now start retrieving the data written by the older container. So that is how you bring persistence to containers. So now we are on to the third demo, dealing with persistence. So now let's actually solve this problem by adding volumes. So there are two ways of dealing with this, right? So let me introduce you to the concept of volumes. So Docker comes with a command called docker volume. And when you actually do an ls, it shows what are the volumes we have. A volume is more implicit. So that means Docker primarily reserves a directory, a space, and when you create a volume, it assigns one of the directories in the designated location as a volume. And you can go ahead and attach this volume to any container that we may launch. So now let's actually go ahead and create a new volume called data. Now, when we actually do a volume ls, we notice that we have a new volume available called data. So this time, when we are actually launching a web server, I have an additional switch that is -v followed by data, which is the volume that we just created, which is mapped to the internal directory structure of the container, which is available as /data. So now when we actually go ahead and launch this container, we'll end up seeing a new directory within the root called data. Let's actually try that. But how do we test it? How do we basically make sure that it is available? Well, I want to introduce you to another command, and that is called docker exec. And docker exec is a very powerful command because it executes a command within the container. So if you, for example, if you run this with something like ls, it'll actually show up, it will show all the files available in the container. Instead of ls or any other command, we can actually invoke the shell, and we pass two parameters to this, I and t. So this is basically saying that make this interactive. That means don't just run it and terminate, and hold it and make it interactive so I can continue to work, and attach the terminal, which means the host terminal will now be able to talk to the shell that is running inside the container. So docker exec followed by -it and the command that you want to run will basically run any command, and we are now invoking the shell of the container, so we'll be dropped right inside the container. So here you'll actually notice that we are at root at the hash of the container. So now when you actually go to the root, you should see a new directory called data. So here, if you create a file, okay, oops, this is not cat, it is echo. I want to create a new file. Okay, now we created a file called test.txt, and when we come out of the container and actually terminate this, so another shortcut, if you want to terminate a container without first stopping, you can always use force docker rm -f followed by the container name. So now we have gone ahead and terminated the container, but guess what? Later on, when you launch the container again and mount the volume, you'll actually notice that the file is preserved. Oops. Okay, we are, okay. So we have launched the container, and now we need to get into the command prompt. So when you actually check this in the new container, this is still available. That's because the volume was attached and it brought back the files that we have saved in the previous session. So this is how you add persistence to containers. Excellent. This is actually more implicit, right? You can also make an explicit directory made available to the host. So let's actually do a fun demo. So what I'm going to do now is to create a local directory called htdocs. Okay, so in my root directory, I have gone ahead and created what is called htdocs. And now when I'm actually running my web server, we are pointing the current directory, $pwd points to the present working directory, followed by htdocs, the directory that I just created. And guess what? We are actually pointing that to Apache's root directory, the document root, which is htdocs. And this is going to make it very interesting. So now when we, okay, I need to get rid of my previous session. So let me run this command again. So we are launching the web server. So now let's get into the container with the same command, docker exec -t followed by the container name bin bash, right? And now we have the htdocs directory and it is empty. So what I'll actually do is to create, I don't want to type a long string, but instead I'll copy and paste this. So we're actually printing hello world from containers and redirecting that into the index.html. So this will create a new index.html with hello world from container. So let's leave this as is, and let's come out and do a curl on localhost. Because we are listening on port 80, this is going to respond with the same text. Perfect. So now we are able to basically serve pages from our web server, and these web pages are actually coming from this directory. So if you're not convinced, let's actually override this. So this time I'm going to do an echo hello world from host. That means we are actually overwriting whatever file was created within the container. And now when we do a, it shows hello world from host. Excellent. So now we are able to run multiple containers. You can launch web 1, web 2, web 3, and all of them can share the same directory exposed by the host, and they have access to the same data. So you can modify it either within the container or outside the container. And if you actually go ahead and get rid of this file with an rm command, guess what? It is also going to get vanished within the container. So it is essentially a shortcut that you created within the container that's pointing to the original directory on the host. And this is how you end up creating persistence. And now you can actually terminate the container, but still keep the data intact. And that is the advantage of having volumes and persistence. Excellent. So now we have learned another concept, which is making containers more useful by bringing in persistence. But it is more powerful to create custom images, right? So for example, I have gone ahead and modified my Apache web server. So I have a new web app installed inside that. So I want to create a new image so that I can distribute it to my customers, friends, family, and they can launch it and they can run it without even knowing how I went about building that application. So this is becoming a very standard way of packaging and deploying applications. So it turns more and more powerful when you get the ability to create custom images running your code. So one thing that you need to understand about creating custom images is you always pull a baseline image from a Docker registry. You don't go about creating, let's say, a Debian image or a RHEL image from a CD. That is not really required because these base images are maintained by the distribution vendors. For example, Red Hat manages the Fedora and CentOS and other images, while Canonical takes care of Ubuntu and some of the other flavors. So you have the option of pulling the official image and building on top of it, because there is no point in reinventing the wheel. You need not build these base images. Instead, you should focus on what's required. For example, if your app is based on Apache and PHP, you can very well start with the Apache HTTPD container and only put your code. So that will make it very easy. Of course, it goes beyond copying files into it. In the next session, I will cover how to build custom Docker files and actually bring your source code into containers. But for now, we'll actually push some static files and package our custom images. So there is a life cycle. You pull the image, then you run the image, you modify the image, and then you commit it to the local file system, go ahead, tag it, and then push it to Docker Hub or Docker Registry. So it's a very well-defined life cycle with very simple set of commands. So let's go ahead and create our first container image. All right. Let me make sure we don't have anything running. I want to get rid of this. So I'll run this command, which is rm with -f web. Okay, so how do we go about building an image? Well, I will start with running the base image with no modifications. This is what we have pulled in the very first demo, that is the Apache web server. So this is running. Next, I go ahead and execute this shell command, which will drop me right inside the container. And after that, I move into the htdocs directory and overwrite the default index.html, right? And that's what is making it as my web app, right? So now we can verify this with a curl localhost. Oops. And this will confirm that we have gone ahead and modified the web application or the web server with our custom web page. But as you know, if we don't commit this, or if we don't turn this into an image and terminate this container, everything will be gone, everything will be vanished. So before anything else happens, I want to first stop the container, because we don't want, for example, in a live environment, we don't want the web server to deal with live connections while we are turning that into an image. So it's always a good idea to stop the container, right? And now when we actually do Docker images, we notice that there are two images on our local machine. One is HTTPD that we are currently dealing with, and the other one is Hello World that we have launched very early in the session. Now, when we actually create our custom image, we'll end up seeing the third one. So let me go ahead and run this command. Docker commit followed by the container name, which is web, followed by do web. So this is my web application compiled on DigitalOcean. So I'm calling it as do web. And when I actually run this, it just confirms with another long string. But to make sure this is indeed turned into an image, we go ahead and run this command, Docker images, and there we go. So you'll actually see that we have gone ahead and committed the container that we modified earlier into a new image called DOWeb. And interestingly, the size of the original HTTPD image and the newly modified image match. That's because we only added a few bytes. It doesn't make much difference. Now, let's say I want all of you to go ahead and launch this container, launch this image to run it as a container. So how do I distribute? As long as it is on my machine, only I can launch that as a container. So to make this available to all of you, I need to actually move it to a more centrally located and centrally available repository. And that's what is Docker Hub. So before I do that, I need to sign up with Docker Hub. For example, I've already signed up, and you can actually notice that it is showing my username, and I can go to my dashboard. There are a lot of Docker images that I've already pushed. So now I want to basically bring DOWeb into my Docker Hub account. So for that, I need to first extend the image name to represent my Docker Hub username followed by the container image name. So what you see here, whatever is put before the slash represents the username of Docker Hub, and that's a convention that Docker follows. For example, if you are launching official images from Microsoft, you'll actually notice that it will be Microsoft/ASP.NET. And if you are launching it from, or launching an image that is coming from MongoDB, you'll actually have the Mongo folks create an image, maybe that will be named as Mongo/MongoDB. So it depends on who the original author and how it is mapped to the Docker Hub account. So now I go ahead and tag this. And tagging is a command that assigns the location of the registry or the username of Docker Hub. Okay, give me a second while I figure out what was the name. Okay, so now it was not web, it was DOWeb. That's what I created. So when I actually do Docker images now, you'll notice that it created another one with my name /DOWeb. And it's actually using the same image. Don't miss this two different images. In fact, it's the same. We just tagged it, which means it is basically creating another shadow of the same image, but this time assigning a username to it. So we have now built an image and also customized it by adding our Docker Hub username to it. Now we can go ahead and push this, but because I'm going to do a push and not a pull, I need to log into the Docker Hub. So I will go ahead and log into Docker Hub by giving my username and password, and this should show succeeded. There we go. So now I've successfully logged into Docker Hub, and the next step is to do the final push. So now I go ahead and push the image that we have tagged earlier, and this is going to take a few seconds. It is basically pushing the image. Since we have based this on Apache HTTPD and that's already there in Docker Hub, only the top layer with our modifications is what is being pushed, and that's it. So now this is officially pushed into Docker Hub, and you can come back and verify it by doing a refresh on my Docker Hub account. And you can also search. There we go. So this is the DO web that I created, and this was last push 3 days ago when I actually tried this, and I only updated. So this is how you end up creating the images and store them in the public repository available on Docker Hub. Perfect. So how do we test it? Well, let's actually go ahead and remove the image. So how do we remove an image? We use the command called RMI. So we first remove HTTPD, right? So let me start with the top level one because it has dependencies. So we first get rid of the top level image that we just built, followed by the one without the tag. And now we are left with just 2 images. We'll also get rid of the HTTPD one. Okay, there are a bunch of containers running in the background that are making use of this. I need to get rid of them before I could completely knock off this image. So that's what I've done here with Docker RM. And now when I actually run this, it is gone. So now Docker images doesn't have anything to do with a web server. Now I can basically run the DO web image that we have built in the previous step and launch it here. And this time I'm not doing a pull, I'm directly using run. So expose port 80, run it in the background. Let's give it a name. Let's call it my web app, what I just built, and then give the image name. And this time I qualify this with the Docker Hub username / image name. So this is now going to pull the image from Docker Hub. It will take just a minute because we are on the DigitalOcean network, which is generally fast. It just pulls the image, extracts all the layers, and now when we do a Docker PS, we notice that my web container based on DO web is running on port 80. So let's go ahead and do a curl, and it should show the customized one. There we go. So welcome to my web application. So pretty cool. So we have now completed another significant step in learning containers, that is creating our custom images. While the changes that we have made look very trivial, you could potentially package a Ruby on Rails app or a Python Flask app or an ASP.NET Core. It doesn't matter. You can follow exactly the same steps to package your application into a container, turn that into an image, push it to Docker Hub, and launch it anywhere. The life cycle remains exactly the same. Just to add the cool factor, because we are running it live in the cloud, I can go back to my droplet, grab the IP address, and run it here. And there we go. In fact, all of you can access this by typing this IP address. And this is a live application that we have just launched. Awesome. So we are left with one final step to complete the session 1. That is the ability to launch a private registry. So now we are familiar with Docker Hub. And I also told you Docker Hub runs in a hosted environment managed by Docker Inc. It would be more powerful and more relevant if we keep our images within our environment without keeping it in the publicly accessible central location. So instead of pushing the images to Docker Hub, how about pushing it to our local registry? So you can launch a Docker Hub-like registry, but running within your VM, or within your cluster, or within your data center. Pull the image from Docker Hub, modify it, test it, and then push it to a private registry. So that will make this very powerful. So the best thing is Docker registry in itself is available as a Docker image. So that means running a Docker registry is as simple as doing a Docker run or Docker pull followed by Docker run. And because we are going to store images, and because it is persistent, and if the container registry terminates and gets killed for some reason, we don't want to lose all the images stored inside that. So we'll apply one of the techniques that we have learned earlier, which is adding persistence and adding storage. So this is a classic example of where volumes become useful and become mandatory for us to run containerized workloads. So the workflow that we follow here is straightforward. We pull a base image from Docker Hub, we run it, we then modify it, we commit that, and finally, instead of actually doing a Docker Hub push, we'll tag the image with the local private registry URL instead of the username of Docker Hub, and then we'll do a Docker push. So these steps are very similar to what we have done earlier, except that we'll target our private registry. So let's learn how to launch a private registry and push images into it. Okay, so I'll take help of my script again. So what we're going to do now, let me make sure we don't have anything running. I want to get rid of this. All right, so let's follow these steps. The very first thing to actually run the private registry is to create a local directory called registry. Ideally, in production environments, you would not do this in the root, but since it's a demo, I'm going ahead and doing it in my home directory. So after the directory is created, we'll run this command. Most of this is familiar to you, docker run -d-p. We are basically exposing port 5000. We're also adding a new switch called restart always, which means we are instructing Docker engine to make sure that it launches this container if it fails with some error, or if it terminates, we want to make sure that it comes back. So we are instructing Docker engine to restart this always every time it is terminated for whatever reason. And then I call this registry, that's the name of the container, -v, the volume, which is pointed to the registry directory that I just created. And it's being pointed to the container location, which is var lib registry. And of course, the images registry, you will actually see registry multiple times, but it means different things in different places. So the registry here is the name that we have given. The registry here is the directory of the host, and this registry is pointing to the directory within the container, and this is the actual image that we are going to pull. So let's go ahead and run this. So once this is executed, we'll end up having a new container running on our machine. And guess what? That is essentially the registry. So Docker PS now shows that this is running for 3 seconds, and we have successfully launched a private registry. So to finish the entire, so Docker pull followed by a very tiny Linux image called BusyBox. BusyBox is a Linux OS that typically powers embedded devices like the routers, switches, various other IP cams, and so on. So BusyBox is a Linux distribution meant for embedded operating system. So we are going to pull that, and the reason why I chose that, it's very tiny in size. So we pull this, and now we have the BusyBox image available on our local machine. So this is now, I think it's just 1 MB, 1.13, not bad. So with that image in place, what I want to do is to push this into my local registry. So I'm not modifying anything. We have seen that earlier. So I'm going ahead and tagging this image called BusyBox that we have pulled in the previous step with localhost :5000. This basically represents the location of Docker registry. If you're targeting Docker Hub, this would be your username. But if you're targeting a private registry, this would typically be the URI of the private registry. And since the URI of this is localhost :5000, we can go ahead and tag this. And once this is tagged, all we got to do is just do a push. Pretty straightforward. Now that's it. So the image is pushed. How do we verify? If you actually go into this directory called registry and look at the multiple directories you have inside, you'll notice it has created multiple directory structures and it contains multiple hashes. So I don't want to dig deeper. It is basically a very nested directory structure that contains the image layers. All right. So now BusyBox has been pulled from Docker Hub. It is tagged and pushed to a private registry. So let's actually do this. I want to show you a shortcut. How do you delete all the images on your machine? So you'll actually use a shortcut from Bash. So basically run Docker images with -a all, -q is quiet, which is the first column. You don't see a lot of details. And then we pass the output to Docker RMI, which will remove every image reported by this. So now this is going to delete most of the images, except the ones that has a running container. So now you'll actually notice that only the registry is running. That's what we want. So now I can do a Docker images, and we notice it's only the registry. And now we're going to pull the image from our local registry that we have just launched. So Docker pull, and we have successfully pulled the image from the local registry to our environment. And it now starts to show up in Docker images command. And you notice that the BusyBox image is now available to us, which is pulled out of the private registry. And as you would have noticed, it is extremely fast. So that basically concludes everything that I wanted to cover in the very first session. We covered a lot of ground, but once you finish watching this and once you get the link to the tutorial, make sure you pause the video at appropriate demos and practice these commands. And the best thing is the tutorial is going to have exactly the same steps in the same sequence and the same commands. So you'll not miss anything. And once you repeat the labs that are going to be a part of the tutorial, you will gain better confidence. So let me go ahead and summarize. Docker makes it easy to deal with containers. You can do containers without Docker, but it only makes it more productive and efficient. Docker has 3 components. Engine, the background process responsible for interfacing with the operating system and exposing the REST API. Tools, the command line tools that we are going to deal with over a period of time. Docker.exe or Docker binary is basically an example of the tools of the client. And the registry that is responsible for holding the images. Docker Hub is a public registry to store images offered free by Docker Inc. You can sign up and push many images to it. Every time you want to run a new image that is not existing or not present on your local host, you basically do a pull from the registry. It could be Docker Hub, it could be local private registry, doesn't matter, but you always need to pull. Volumes bring persistence to containers. Without volumes, you're dealing with stateless ephemeral containers, not very useful. So custom images can be built from base Docker images, like the way we pulled HTTPD, modified it, and created a custom image of it. Private registry keeps the images secure and closer to the engine, thus reducing the latency. Ultimately, you will have better response times for pull and push because the registry lives next to the Docker engine. And things that I didn't cover but you can absolutely implement is leveraging some of the native features of DigitalOcean platform like block storage. For example, you can mount block storage in your droplet and point a volume to it So you have a better availability. So now if the container dies, the storage is attached to the droplet, and if the droplet dies, the storage is now pointing to a block storage device. So you can bring back the VM, you can bring back the container, and everything is going to be intact. So it offers better durability and better level of persistence. So I encourage you to consider using DigitalOcean's block storage when you are mounting volumes. And similarly, when you want to protect and secure your container deployments, as a first line of defense, configure DigitalOcean's firewall. For example, you don't want everyone to hit your private registry, so you can basically block every port except port 80. And you can also implement some advanced rules that will ensure that your droplet is protected. So you can get additional level of security by configuring a firewall. So those are the key points that I covered in today's session. I want to leave you with a set of commands. I'm not going to recap all of them, but they will be made available to you in the tutorial. And this is a quick reference. As you notice, we covered quite a few commands. Docker save and Docker load are bonus commands that I didn't cover, but you can explore. They basically help you to export and import container images. So if you don't want to push an image, but copy it to a thumb drive and hand it over to your friend, you can actually use Docker save instead of taking the route of a registry. So it turns your image into a tar file. You can copy the tar file to any USB drive, and at the destination, you basically do a Docker load, and it imports the container image. So it's a nice exercise for you to try out. So various commands that I covered today will help you get mastery over Docker. So that brings us to the end of this session. It's not the actual end. We have pretty exciting sessions lined up for the next 5 months. So do stay tuned.